Okay, the purpose of this video is to go over unit goal 7 of our sequence and series unit. Basically, unit goal 7 is how we're going to be able to calculate the sum of an infinite geometric series. So we haven't talked about an actual infinite series, that is adding up the entire series. There's a reason we haven't talked about that, so I'll talk about what it actually means to add up the entire series. And then why are we actually going to get a value? Because it sounds like, well, if you add up infinite things, you're going to go to infinity, so why is this even a topic? Well, I'll show you that there's actually a special case where an infinite geometric series will actually give us a finite number. So let's discuss what all of this means. And once again, there'll be one more formula to help us conquer this. So remember, a series is when you take a sequence being a list of numbers. If you take a sequence goes on forever. So a series adds up a sequence. What happens if you add up the series forever? Since the sequence goes on forever, you can just keep adding and adding and adding. Now, if it's just some random sequence, well, you'd have to have all the values. But we've been talking about arithmetic sequences and geometric sequences. And then from them, we can make an arithmetic series or geometric series. Now, when we did the arithmetic series, so here's an example of an arithmetic series. The reason we never talked about this going on forever is because it's ridiculous to talk about that, right? So here's an arithmetic sequence added up becomes an arithmetic series. Now, if I don't cut this off, if I say add up the first like 5 terms or 7 terms, I get a number. But if I say add them all up, well, the answer just gets infinitely big. So if I just keep adding these 7 plus 10 plus 13 plus 16, so hopefully you see the common difference is 3. Next one would be 19. Next one would be 22. Clearly, if I add them up forever, I'm going to get infinity, and I'm not going to get a number. This actually happens with all arithmetic sequences and series. Arithmetic ones either go up forever, or you could have a negative common difference, and then they just go kind of down forever, and they become negatively large, and they add up to negative infinity. So we didn't really talk about this infinite thing for arithmetic series, because arithmetic series always add up to either infinity or negative infinity. Now, with geometric series, something interesting happens. Now, not all geometric series. So here's a geometric series. It's formed from a geometric sequence. Remember, geometric means that instead of, like here, they add by 3. In geometric, they multiply by the same number. So these are all doubling. So multiply by 2, multiply by 2, multiply by 2. The next one would be 48. The next one would be 96, and so on. Clearly, if I add all these up, I get the same problem. The thing goes on, this adds up to infinity. But the thing with geometric series is it's actually possible to make a geometric series that doesn't add up to infinity. So that's why we need to go over this unit, this unit goal, is because unlike arithmetic ones that always added up to something infinite, geometric ones don't. So this is actually a bad example for what I'm trying to talk about, because you look at this, you go, well, this adds up to infinity also. Let me talk about one that doesn't add up to infinity, and I'll illustrate it, hopefully with a simple picture. So here's a football field. If you know about football, then you know how big the football field is. If not, I'll explain it really quickly. This is where you make your touchdown, like your end zones. Basically, from this line to this line is a total of 100 yards. Now, when they label on the football field, they label them up to 50, and then they start counting back down. But basically, if you go from one side to the other, when you hit 50, this is basically 60, 70, 80, 90, and then 100. So there are 100 yards on here. Now, I drew a little person up here because this little person's going to walk the football field. But they're going to walk it in a special way. So they're going to start at the goal line, and they're going to try to get to the other goal line. But I'm going to make this person, as they walk, they're going to walk half the field. And then when they stop, they are going to walk half of what's left. And then they're going to stop and walk half of what's left. And they're going to keep doing this, and we'll see how far they get. So I'm going to start here. The first person's step is going to be to start here and then walk half the field. So I'm going to let them walk half the field, and then I'm going to have them stop. So they walk half the field. They've walked a total of 50 yards. Now, in their next step, they're going to walk half of what they did before, or half of what's left. So half of what's left, well, there's 50 yards left. I'm requiring that they're only going to walk half of that. So if they walk half of what's left, 50's left, half of 50's 25. So they're going to walk 25 yards, and then that's their second trip. So first trip got them the 50, second trip gets them the 25. Now, they got to keep walking according to my requirements. So I'm going to require that they now go half the distance again. So if they go half the distance again, well, half of 25 is 12.5. So they're going to walk 12.5 yards, and they're going to end up here. Now, in their next step, they're going to walk half of that distance. Half of 12.5 is 6.25. So they're going to walk 6.25 yards. And now you start to get the idea, if I keep cutting this in half, half of 6.25 is 3.125. So they're going to walk about 3-something yards. Now, I'm not going to do it exactly, but half of 3 is about 1.5. They'll walk 1.5 yards. Then they're going to walk 3/4 of a yard. Then they're going to walk 3/8 of a yard. And every time they go on, they're walking less and less and less and less. In fact, notice I keep cutting in half. So they've gone half the field, half the field, half the field, half. If I have them do this forever, if they keep going half the field, they can do this forever, and they never actually make it to the goal line. So now this is kind of a silly thing to do. Why would somebody do this? But this actually was actually a paradox formulated in ancient Greece. There was this guy Zeno, and he basically said, what if I went half the distance in a room and then went half the distance again and half the distance, half the distance? He claimed doing that you'd never leave the room because every time there's always a little bit of distance left, and you're cutting that distance in half, and you're leaving a little more, and you're leaving a little more, and you're leaving a little more. And if you walk in this manner, you never actually make it to the goal line. You get infinitely close to here. So basically, the point of this is that this person can do this procedure forever, but they don't travel infinite distance. The farthest they ever get is to the edge of the football field. So under this procedure, they can't ever go over 100 yards. So what does this look like? Well, basically, the way I made this person walk is a geometric sequence, and then their total distance is a geometric series. I had them walk 50 yards the first time. Then I had them walk 25 yards. Then I had them walk 12.5 yards. Then I had them walk 6.25 yards. Notice this is a geometric sequence. Each member's half of the other one. So the common ratio here is a half. If I keep cutting these in half forever, if the person gets closer and closer and closer to the full football field, they never actually at any moment will make it to the football field. But what we say is, as we add these up, we get closer and closer and closer and closer to a certain value. The maximum value that we approach is 100. So notice that this is an infinite sequence, but it doesn't add up to infinity. So that adds up to infinity. That's arithmetic. That adds up to infinity. It's geometric. This doesn't, even though there's an infinite number of terms, it doesn't add up to infinity. It adds up to at most 100. So this is a geometric sequence that if I make the series out of it, I can actually add it up forever and I don't get infinity. I actually start to approach an actual number. So the question for this unit is, number one, why does this happen in this example? Why does this geometric sequence add up to a number where this geometric sequence added up to infinity? So basically we need to see like when some of these will add up to infinity and others will add up to a number, like the football field example does. When does that happen and why? And then once we determine that, like this case, a geometric series does add up to a number, how do we calculate that number? I use the football field example because I think if, it hopefully makes logical sense. If you keep going half and 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 so on, the farthest this guy could ever go is the 100 yards. Like he's never able to, by the procedure I gave him, he's never able to get into the end zone. So I'm only coming up with this number through this example logically. I'm kind of going, well, he's got to go 100. But if I didn't give you this and didn't give you this, sort of, I think, nicely visual example of what's going on, You might not know what this all is supposed to add up to. So we want a formula to do this. So let's talk about what they call these. So if you add up forever and you get something that becomes infinite, it's called a divergent series. So a divergent series is a series whose value becomes infinite the farther you go. So if you're just going to keep going, the thing never approaches anything, that would be divergent. The opposite of a divergent series is a convergent series. A convergent series converges onto something. So a convergent series is a series that gets arbitrarily close to a value as you add more and more and more terms. So these two are divergent. As you keep adding, the number keeps getting larger and larger and larger without bound. This one, however, is a convergent series because as I add more and more and more and more, it gets closer and closer and closer and closer to 100. So I'm not going to pull out a calculator, but if you started adding these up, you'll find out that you'll get up to 98, you'll get up to 99, you get up to 99.5, then you get up to 99.9999, but you'll never get beyond 100. So if you continue this series on and on and on, you're approaching that number. All right? So the question is, how do we know if a series is divergent or convergent? All arithmetic series are divergent. That's why we haven't talked about it yet. So when I did the arithmetic ones, there was no reason to make this distinction. However, the geometric ones, the idea of the geometric ones is if the geometric series is growing larger, it diverges. If the series is getting smaller, it's possible, it doesn't always, but it's possible that it converges. So the difference between this football field example and the other one is that notice that these are shrinking. They're shrinking fast enough that they don't allow this thing to add up to any more than the football field itself. They're just shrinking too quickly. Even though I'm going to add up an infinite number of them, they become so tiny. Because remember, after this is 3.125, and then it's like probably 1.6 something or other. Then cut that in half, you'd be at 0.8 something or other, and they just get super tiny. All right. So even though we're adding up a lot of them, they shrink. So if they're shrinking, we need to have a standard for when this will happen. And once we know this will happen, we need a formula to figure out what the value is. All right. So we had this formula for adding up a geometric series through the nth term. So the nth term would be like if I wanted to add the first 12 or the first 20 or the first 100. And this is what the last unit goal was about. So if you did that assignment and watched that video, you would have seen this notation. You would have done this assignment. You would know, oh, if I want up the first 20 terms, I need the first term, the common ratio, and that n value is given to me. Basically, I want a formula for what if I want to add up all the values. Now, if I want to add up all the values, I first need to answer the question is that a meaningful thing to ask? If it's divergent, then no, there's not going to be any value. But if it's convergent, if it's going to converge onto something, it'd be nice to know how to calculate that. So basically, how do we know if it's convergent? If it is convergent, what's the formula? Well, here's how we know if it's convergent. Convergence depends on the common ratio. Basically, there's a nice sweet spot for the common ratio. If the common ratio is a number that's in the red section, basically numbers bigger than 1 or less than -1, then the thing diverges. So the red is kind of bad. If your common ratio is in the red, you're divergent. So let's go back and look. This was divergent because its common ratio is 2, right? You're doubling, doubling, doubling. Since the common ratio is 2, 2 is in the red. So that means that the thing is going to diverge. If it's divergent, there's no reason to answer the question. There is no answer. It becomes infinite. However, if you're in this blue range, and notice I leave open dots here because 1 and -1 are not included with the blue. If you're between 1 and -1, your R value, if your R is between 1 and -1, what that does is it shrinks your terms. If you're shrinking your terms, then you won't add up in a geometric sense to infinity. So basically, if your R is in this sweet spot, that's what this says. If the R is in the blue region, then the infinite series will actually converge. So that magic range is if your R value is bigger than -1, but less than, oops, we got R here twice, less than 1. Fix that. Typos are bad. All right. So if you're between 1 and -1, basically all the kind of tiny decimals and fractions. So why was the football series convergent? Well, it's convergent because its common ratio is 1/2 or 0.5, right? Multiply by 0.5, 0.5, 0.5, 0.5. Well, if you multiply by 0.5, you're right here, and that means that your series will converge. So if your series is convergent, now you know when it does and when it doesn't. Basically, look at the common ratio and see if it's in this section here. If it is, you'll converge. If you converge, you need a value. What's your value? Well, time to give you the formula. So how do you figure out what the value is? It ends up, it's a simplified version of this, believe it or not. If we were a class, I'd explain how this turns into this. But these videos, it's not so easy to do that. So I'll just give you the formula. Basically, if you want to add up all of the terms, and you know it converges, meaning your R is between 1 and -1, then this formula will give you what it adds up to. And notice it's actually easier than this formula. That's why I always thought it was funny. It's actually more difficult to add up 20 terms than it is for the formula to add up infinite terms. Basically, by making this n infinity, if the R is a tiny number, this whole thing just kind of goes away and it drops into this. So if you're an honors person or something and you study some calculus, we'll talk about this more in detail. For now, you don't really need to know where it comes from. You can just use this formula. So this formula says if you want to add up all the terms and you know the geometric series converges, all you need is the first term and the common ratio. You plug them in and it'll tell you what it adds up to. So I'll give you a couple examples and then I'll do the football field and show you how it actually confirms our intuition for that. All right. So let's look at this. Let's do a piece at a time here. So say they want you to find the sum of this sequence. And when they put the ... it means they don't want you to stop. They want you to sum up this entire thing. So the reason you can't answer this by hand is you clearly don't want to try to add these up forever. You can't add them up forever. You don't have enough time to sit here and do it by hand. That's why the formula does it for us. So if we add 1 to 1/3 to 1/9 to 1/27, blah, 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 this is, so long as it's a geometric series and the common ratio is between 1 and -1, we can do it. So let's just verify that. Well, the common ratio here is 1/3. Basically, 1 to here, you got to divide 3 or multiply by 1/3. If you multiply by 1/3 again, you get 1/9. Multiply by 1/3 again, you get 1/27. Remember, you can always take a term and divide it by the one before it to get the common ratio. So if I put in a calculator 1/3 divide 1, it would give me the common ratio. Or you can just look at the fractions and realize, well, the top gets multiplied by 1, but the bottom gets multiplied by 3. So it's going to be 1/3. In order to use this formula, say I want to know what all of them add up to, or what they approach as you keep adding them. Well, I'd use this formula. To use this formula to add up the entire list, I need the first term and the common ratio. So I know the first term is 1, and the common ratio I just determined was 1/3. So if I plug those in, let's just get rid of this now. First term is 1. That one's just part of the formula, and R is 1/3. Calculate what that is. Well, 1 in the top, 1 minus 1/3 is a total of 2/3. And 1 divide 2/3, when you divide by a fraction, you multiply by the reciprocal, and you get 3/2. Now, you can do this by hand, or if you're not that kind of person where you don't like to calculate stuff, you can just, if you're careful, throw this into a calculator. Make sure that you have parentheses and everything in the right spot. But if you throw this into the calculator, it'll give you that answer of 3/2, or 1.5. So basically, what does all of this add up to? The more you add these, the closer and closer and closer you'll get to 1.5, or 3/2. And in theory, if you added up the entire list, if you had an infinite time to sit around adding that thing up, it would eventually just approach and then, I don't want to say reach, but essentially limits out at 1.5. So this thing does not add up to be infinite. It adds up to be 1.5 as you carry it out further and further. Look at one more example. Let me cover it up to show you the part you'd see. So on your homework, you might see a problem that looks like this. Remember, this is just fancy notation for saying to add things up. So this is the summation sign, the Greek letter sigma. It just means add up this sequence. Now, the reason this one's more difficult is it tells you to start from term 1 and go up to term infinity, right? So it tells you to add up forever. Once again, not something you can do by hand unless you know this formula. Now, this thing looks really intimidating because it goes add up all this stuff, and these things look weird. But the easiest way to handle it is to actually turn it into a problem that looks like this. So how do you do that? Well, start plugging in some numbers. If you plug in 1 for I, plug in 2 for I, plug in 3 for I, you don't have to go all the way up to infinity. Once you plug in a couple numbers, you'll start to see what the sequence looks like. So if I plug in 1, I get 1 minus 1, which is 0. Anything to the power of 0 is 1. So I'll just get negative 3/4. What's the second term? Well, if I plug in 2, which is the next number, plug in 2. 2 minus 1 is 1. This to the power of 1 would be this number. So my second term would be negative 1/2 times negative 3/4, which comes out as positive 3/8. This is actually enough information to answer the question now, but I'll go one step further. Say I wanted the third term. I'd plug a 3 in here. 3 minus 1 is 2. If I put a calculator or by hand did negative 1/2 squared, I get a positive 1/4. Positive 1/4 times negative 3/4 would be negative 3/16, and so on. So here's the good news. Once I make a couple of these terms, I just need to find the common ratio and the first term, right? So what's the first term? Well, I just plugged in 1 and found it, negative 3/4. Now, what's the common ratio? The easiest way to get it is to see, well, what do I multiply by? Notice that the top stays 3. So 3, 3, 3 means I'm multiplying the top by 1. Now, you might notice that there's the negative sign alternating. Since it's alternating, technically I'm going negative, positive, negative, positive. So I'm going to include a negative in this. So the top is actually being multiplied by negative 1. Negative 3 times negative 1 is 3, times negative 1 is negative 3, and so on. So if I look at the bottom, 4 to 8 is doubling, right? So double 4 to 8, double 8 to 16. The bottom is doubling. So if you just look at what's happening to the top and what's happening to the bottom, you create the common ratio. Basically, I need to multiply each term by negative 1 over 2 to get to the next one. If I multiply this by negative 1 over 2, I get this. Multiply this by negative 1 over 2, I get this. If I did it again, another negative 1 would turn this to 3, and 2 would turn this into 32. So the next term would be 3 over 32. Basically, I don't need to know that. In order to add up the entire sequence, I just need to know the first term and the common ratio. Plug those in. The first term is negative 3/4. The common ratio is negative 1/2. Once again, if you don't like doing calculations, be very careful that you plug this in the calculator correctly. I just showed some of the intermediate steps. The top is negative 3/4. 1 minus negative 1/2 is 1 plus 1/2. 1 plus 1/2 is 3/2. If you do this, divide this, you could multiply by the reciprocal. It'll come out as negative 1/2 or negative 0.5. So basically, what does all of this add up to if I kept going forever? It basically adds up to or approaches the number negative 0.5 or negative 1/2, depends on how you want to put it. So that's the answer to this thing. What is the value of this? This is basically asking, what happens if I plug in 1, 2, 3, all the way up to infinity, if I make infinite terms? If I make infinite terms, they all look like this. And if they all look like this formula tells me what they added up to. All right? So I'll end back with the football example to show you that intuition told us the football example would add up to 100. I'll show you this formula does support that. The football example, remember, was the person would walk half the football field and then half of what was left and half of what was left and half of what was left. So basically, I wanted to add up 50 plus 25 plus 12.5 plus 6.25 plus 3.125, blah, 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 blah. What is all of this added up? It was supposed to come out as 100. So notice this formula will give you that. What is the sum of this entire geometric sequence? Well, the common ratio is in that range, so make sure you check that. If the common ratio is bigger than 1 or less than -1, you wouldn't bother doing the problem. The common ratio is a half. The first term is 50. Plug in the first term in the common ratio. It's 50 over 1 minus a half. 1 minus 1/2 is actually a half. And then 50 divided a half is the same as multiplying by the reciprocal, 50 times 2, which is 100. So notice that it actually solves a football field example for us without us having to really think of it like a football field. Basically, 50 plus 25 plus 12.5 on and on and on. The farther you go, the closer you get to 100, and this formula shows that our intuition's correct. Or basically our intuition also supports this formula, all right? So this was infinite geometric series. The summary was basically use this formula. Only use the formula if the R value is in here. So if your R value is like, like we had in these problems, a half or whatever else we had. I mean, let's go back and look. Here we had 1/3. Here we had negative a half, and in the other one we had positive a half. So notice all of those values were in this blue range. If your R is outside the blue range, you don't get an answer, or you get like infinity for your answer. Also realize you only have to do this with geometric series. Arithmetic series don't work this way. Arithmetic series always diverge. So basically you're looking for, if your R is in here, then you can, go the right way, then you can use this formula. And it'll add everything up for you. So what's kind of cool is one simple formula essentially does infinite work for you. Not bad for one simple formula like that. All right, the assignment's in here. Try it out. Until next time, stay safe.